In this section, we're going to learn the normal distribution. It is a very important topic that we will use throughout the entire semester. Thus far, we have been dealing with discrete distributions. We can also classify random variables as continuous. For variables that are measured, such as heights and weights. Recall for discrete distributions, the area under the histogram was equal to the probability. For a discrete distribution, we have rectangles for our histogram, and if we add up all of the rectangles, the total area has to be equal to 1. But something that is discrete is countable. You could count 0, 1, 2, 3, and so on. But something that's continuous, that's not possible. You have a range of infinite values with no gaps in between. For continuous distributions, area equals probability as well. That's a very important concept. The area is always equal to 1 because that represents 100%. However, instead of drawing probability histograms, we draw smooth curves. In truth, to find the area under the curve involves calculus. However, we will utilize a table to find these probabilities, so you don't have to know anything about calculus. The graph of the normal distribution is perfectly bell-shaped. It's perfectly bell-shaped, just like when we were doing the empirical rule or the normal rule. We're talking about a diagram that's perfectly symmetrical and bell-shaped. Mu locates the center of the distribution. Since our figure is perfectly symmetric, we have the mean is in the center of the distribution. And sigma determines how spread out the distribution is. So to the right side of the distribution, we have mu plus sigma. Go further out, we have mu plus 2 sigma. And then at the far end, we have mu plus 3 sigma. 3 standard deviations away from the center. Similarly, on the left side, we have mu minus sigma, mu minus 2 sigma, and on the far left, we have mu minus 3 sigma. So 3 standard deviations away from the center. The total area under the curve is 1, so 50% of the data is above the mean, and 50% of it is below the mean. Here we have 50% of the data that's below the mean, and another 50% of the data that's above the mean. Details of the distribution extend forever. They never touch the horizontal axis. If you have ever taken Algebra 2, you will realize the horizontal line down here is an asymptote, which means the graph approaches it forever but never touches the horizontal axis. A normal distribution with mean of 0 and standard deviation 1 is called a standard normal distribution and is denoted with the letter Z. The table printed in the back of the text is for standard normal distribution. All other normally distributed random variables will need to be converted to this standard normal distribution. We will use a table for some problems, and you can also use the statistics calculator that's provided in the description. If you look at the normal distribution, the mean is equal to 0 is in the center. That's 50% of the data is going to be to the left of it, and 50% of the data is going to be to the right of it. We have -1, -2, and -3, which means it's 3 standard deviations below the mean, 2 standard deviations below the mean, and 1 standard deviation below the mean. To the right side, we have positive values, 1, 2, and 3. This represents 1 standard deviation above the mean, 2 standard deviations above the mean, and 3 standard deviations above the mean. So on the left side of the center, we have negative values. On the right side of center, we have positive values. The z-table always gives the area to the left. That's very important. Every single z-table always gives the area to the left. If you have a negative z value, you will notice since our mean is 0 in the center, the area will be less than 50%. If the z value is positive, our area is going to be greater than 50% because z is, of course, in the center again. Let's learn how to use the z-table. The area under the normal standard curve to the left of z equals 1.33 is 0.9082. Let's figure out how to use the table. We have to look at the first two numbers, 1.3. I'll look at the column here, and I'll locate 1.3. And the last digit here is a 3, so we'll find 0.03 on the column and intersect the row of 1.3 with the column of 0.03, and there is our area, 0.9082. What does 0.9082 represent? Well, if I draw a picture of the standard normal distribution, we have the mean is 0. 1.3 is going to be somewhere to the right side of that, and we have an area of 0.9082 to the left of that. Remember, for the z-table, the area is always to the left. So this area in the shaded region is equal to 0.9082. There are three cases to consider. Since our table always gives the area to the left of the z, there are three cases to consider since our table always gives us the area to the left of z. Please find the following values. In these problems, we're going to look at the less than case. So all of these are less than or equal. For the first one, we want to find the probability of z to the left of negative 1.25. So we'll go to our table. In our z-table, there's two sides to it. There's a negative side, and then there's a positive side. Look at the z-score. It will be positive or it will be negative. I'm going to use the negative side, negative 1.2, and I want to have the column of 0.05, and we'll intersect the column and the row. We should get 0.0156. This is equal to 0.1056. For the second problem, we have the probability of z is less than or equal to 2.45. I'll locate 2.45 in the row and find 0.05 in the column. For this question, we're going to locate 2.4 for the row and 0.05 for the column. And we'll intersect the row and column. And there you go. This is our solution. Our solution is 0.9929. And so the area to the left is 0.9929. For problem 3, we want to find the probability of z less than 0.19. And we'll go to the table again. We're going to look at the row that says 0.1 and the column that says 0.09. And here is our solution. Our solution is 0.5753. Our solution again is 0.5753. All of these represent the less than case, so they represent the area on the left. Part B, we're looking at the greater than case, and all of these represent the area to the right of the z-score. Now, how are we going to find the area to the right of 1.87 if the table only gives us the area to the left? Here's what we're going to have to do. We know the area is going to be given to the left, and that's going to be the area here in blue. I want the area in red, but I know something else. The total area is equal to 1. That means if I want to find the area to the right, all I have to do is subtract 1 minus the area to the left. And that's going to give me the area on the right. And that's what we're going to do. We'll look at 1.8 and 0.07 for the column, 1.8 for the row, and 0.07 for the column. This gives us an area of 0.9693. This gives us an area to the left of 0.9693. But remember, that's not the area I want. I want the area on the right. So we'll subtract from 1. 1 minus 0.9693. And so our area is equal to 0.0307. This is the area to the right of 1.87. For the probability of z greater than or equal to negative 0.05, we're also looking for the area to the right. So we'll take our number and we'll subtract it from 1. Find the area to the left of negative 0.05 and subtract that from 1. We have negative 0.05. So I'm going to look at negative 0.0. And we want to look at the column that says 0.05. So our area is down here, 0.4801. Our area to the left is 0.4801. And to find the area to the right, we'll have to subtract from 1. And this gives us an area of 0.5199. In part C, I'm looking at the in-between case. That's the situation where I want to find the area between two z-scores. And in order to figure out the area between the two z-scores, we'll have to do some subtraction. Remember, our table always gives the area to the left, so I'm going to look at the bigger z-score and find that area to the left of that. And that area is going to be way too big. I need to subtract the part that I don't want. So we're going to find the area of the part we don't want to the left of this smaller z, and we'll subtract the bigger number by the smaller number, and we should get the area that we do want, the middle part. In question number 1, we want to find the area between negative 3.00 and 3.00. I'll look at negative 3.00, and the area is 0.0013. And we'll look at positive 3.00, and that's going to give us an area of 0.9987. We will take 0.9987 and subtract 0.0013. This gives us the area between these two numbers as 0.9974. In example 2, 3, and 4, I want you to try those on your own. Pause the video and try it on your own using the z-table. The area to the left of negative 1.0 is 0.1587, and the area to the left of 1.0 is 0.8413. So we'll take the bigger and subtract the smaller again. This gives us 0.8413 minus 0.1587 from our z-table. And so the area between these two numbers is 0.6826. In example 3, we'll try between negative 1.96 and positive 1.96. Negative 1.9, and we need to locate the column 0.06. So the area to the left of negative 1.96 is 0.0250. And for the positive side, we have 1.9 here for the row, and the column 0.06. And if we intersect the row and the column, we get the area is 0.9750. To find the area between, we just have to subtract the bigger area minus the smaller area, and we should get 0.95. Now these numbers should look familiar to you. I want you to notice that this is approximately 99.7%, this is approximately 68%, and this is 95%. Do those numbers ring a bell? 68%, 95%, and 99.7%. These numbers are from the normal rule. And remember, within 3 standard deviations is 99.7% of the data. Within 1 standard deviation, it's 68% of the data. And between 2 standard deviations is approximately 95% of the data. So that's where these numbers come from. So they relate to the normal rule. So the last problem, we'll go to negative 1.19. And so that's negative 1.1 for the row and 0.09 for the column. So our area is 0.1170. And now we'll look for negative 0.17. The row is negative 0.1 and the column is 0.7. So the two areas that we need are 0.1170 and 0.4325. I have 0.4325 is subtracted by 0.1170, and this gives us an area between the two curves of 0.3155. So if we want to find the area between the two curves, subtract the area of the bigger minus the area of the smaller. If we want to find the area to the right, we always subtract from 1. And if it's just area to the left, we just use the table. Note, since z is continuous, the probability of z greater than 1.87 is equivalent to the probability of z greater than or equal to 1.87. So don't worry about the symbol greater than or equal. They will yield the same area. You only need to worry about that when you're talking about discrete distribution, such as the binomial and the Poisson distribution.